In this module, I will introduce transfer function and how to represent the transfer function in MATLAB, and also analyze the transfer function properties, and also get the step and impulse response of single input, single outputs linear systems, and also how to build your own input and get a response. And finally, I will show you how to get the transient characteristic of the linear dynamic system and using some function here. So you're going to run all this function in this module, and also before you watch this module, you should watch all these 4 modules. Otherwise, it will be challenging for you to understand this module, right? Especially you should know what is Laplace transform before you watch this module. So I will use one example here to show you how to handle all these transfer functions problems. So here we focus on the lip boiler in the distillation column, right? So here is the diagram. So we change the electrical power, right? Q is lowercase q is electrical power, and then the electrical power is changed to heating power, right? Capital Q, and then the heating power heat up the steam generator, and then we change the steam pressure, and then the steam pressure will change the liquid level in the boiler, right? So here is the liquid level in the boiler, for example L. So right, something like this. So we represent the system using this diagram, and we link the input with the lowercase q electrical power to the output liquid level, and we call this is a transfer function here, right? So this transfer function, this the input, and this the output, right? The transfer function is pretty important here. The reason is I want to give you some background, right? For example, you want to study whether the system is stable. For example, if you change the Q, the input, right, what happens to the output? Is the output L still stable? And also, if we had a change in the steady state value of Q, the input, what is the change of the steady state value of the output, right? And also, we want to also get the, based on the transfer function, we could predict the profile of L, and then based on that, we could predict some safety issue, right? And also, also can use it and to evaluate the performance of the controller. Also, we could get controller evaluation. Okay, now what's transfer function? I believe you learned it from the process control or systems engineering courses. Here, just give you a very brief introduction. So I believe you know this is ODE model, right? So this ODE, and then we have the time t as the variable here. We got time domain, and then after we do the Laplace transform, we could get the Laplace domain. So here, so we don't have t anymore, we only have s. Alright, this in the time domain we have t, in the Laplace domain we have s, and then you can see this equation actually is algebra equation, right? So and then we get the output, y is output, u is input, and then we call this one as transfer function, right? So this g transfer function actually is equally represented as ns is the numerator term, and then ds the denominator term, right? So you get is the output, equal to the input times G. So this U is the input, right? So G is the transfer function. So you can see the transfer function is pretty important because it links the input to the output, and also it can use to predict the output profile for the specified input profile, right? So you can see the transfer function just like the algebra format right here of the old in the Laplace domain in the algebra equation. Okay, so hopefully you have some idea of what the transfer function look like here. And so for example, for this ODE model, and then we can get the Laplace transform. LT means Laplace transform, right? We can get this general format of the transfer function, like NS numerator term, DS denominator term, and then we also can represent the transfer function using the pole and zero format. So the zero means what? The zero, right, is the root of the denominator. So this is the root. Actually, it's the root of the numerator. So this is the root, right? And then we call Z1 to Zn. Okay. So we call this a 0. So similarly, the poles actually is right, is the root of the denominator. Again, we call this a pole. Okay, this is zeros. So we can represent the transfer function using this format. So another format we call time constant. Here's tau z, tau p, the time constant. The time constant is important, right? And because it could predict the response speed. You should learn this from the process control class or systems engineering, dynamic system. And K is the steady state game of the system. So the K is important because K can predict the change of the steady state of output from the change of the steady state of the input. Okay, so now I want to show you how to represent the transfer function in MATLAB, and using two functions TF and ZPK means the zero pole and K is the game. Now I want to show you the TF. The TF one is the most commonly used function. So the TF means we're going to show, so this TF, so this is the coefficient, right, in the of the S terms in the numerator, and then this is the coefficient, right, in the denominator of the transfer function. So therefore we just expand by the these three terms together, right, to get a coefficient. So here's, remember this is the original ODE, right? So we need to expand the numerator, and also we need to expand the denominators to get all the coefficients. So for the numerator, it's very simple, right? You get -2 and 2, right? And then for the denominator, and then we could use this function, this code in MATLAB to get the coefficient. Okay, so you get just define a symbolic variable s, and then you get expand, then you get its coefficient. Right? This is written in the denominator, right here. It is written in the denominator. Okay, now so after that, then you get a coefficient here. I want to show you. Okay, so we're going to build a new function. Well, actually, a new script here to record all the commands I'm going to type. So I save it. So it's the main TF transfer function. So I say hey, symbolic 6 operation, and then expand. Right here should be so when type the places, you should type the places in pairs. Alright, so we have 3. Turn here. Then the first one you get 0.5 times s plus 1. The second one is 3 times s plus 1. The last one is 5 times s plus 1. So save it, and then you're gonna run here, run it, and then see, here's the coefficient, right? You get coefficient for the cubic term is 15/2. Then this would be for the square term is 19, and for the s term is 17/2, and then you get 1. So actually it's this one, right? It's exactly the same. Okay, now let's type this in. Okay, after we get this coefficient, and then we don't need them, right? So you just keep the control, and then to block this these 2 lines here. So what you can do now is you're going to type the transfer function in. You get systems 1 equal transfer function, right? So remember the coefficient in the numerator is what? Right, I'll show you again. Should be -2 and 2, right? Here. So I'm going to type. So in the numerator you get -2 and 2, and the denominator you're gonna get you put a comma here. Denominator you're gonna get 15/2, 19, right? And then so you can see the coefficients from the higher order to lower order, right? So you get 2 and then 1. Okay, save it, and then you can just click run. See, this is the transfer function you're gonna get, right? Okay, exactly the same as this one. Okay, now I want to show you how to use the ZPK function to represent the transfer function. So Z means 0, P means pro, and K means the game. So we have to represent the transfer function in this standard format, right? So now I'll rewrite the equation for you here. So we get L. Remember, so the transfer function actually equal to 2 minus s plus 1, and then 0.5s plus 1, 3s plus 1, then this 5s plus 1, right? Okay, now let's take a look at the standard format. You will see the coefficient of s should be 1. So, but you can see this is not 1, this is not 1, this is not 1, but this is not 1 too. So therefore we just change it, right? So we change it. So to make this coefficient equal to 1, so we need times -1. Here we need times 2. This we times 1/3. This 1/5. So we get 2. So you can times -1, and then you get s -1. And you can this one you could times in the denominator you can times 2. So you get s plus 2, right? And then in the numerator you also need to times the 2, right, to get the balance. And this one you can times 1/3, so you get s. So 1/3 times 1 equal to 1/3. So you times here you can times 1/3. So similarly, the last one you get s times so you did times 1/5, right? So this s plus 1 times 1/5 equal to 1/5. So this time you times 1/5 in the denominator, right? You also need times 1/5 in the numerator. So therefore, this the standard format you're going to get, and all this is the game, right? in the 0 pole and format, right? So you can see the 0 is what? The 0 is this turn equal to 0, and then you get 0 equal to 1, so this is 0. And then the poles is equal to 0, right? The poles for this one is -2, this one is -3, right? You set this turn equal to 0, right? So you get the poles -1/3. Similarly, this turn equal to 0, we get the pole equal to -1/5. So this Z, this is the K, P, right? And then this is the K. K is this one, right? It's 2 -2 here, right? This is -2, -2, 2, and 1/3 and 1/5. Okay, so we can just type it, and then we could get it, right? Z1 as 6, but this model should be the same as the one we get using using the TF function, right? Just they look different, but they should be the same, right? So you get ZPK. The 0 is 1, right? Then it's written here. This one is the pole is -1, -1/3. This one is -1/5. And then the game should be because it only have one turn, so we don't need the parentheses. So 2 times 1/3 times 1/5 times -2. Okay, save it, right? And then you run it. So you should get system 1, system 2. So this system 2 here, right? So it should be exact the same as the one we have here now, here, right here. Okay, the same as this one. Okay, now you know how to represent the transfer function in MATLAB. Now let's do some analysis of the transfer function. For example, we want to get a pose 0, the starter state game, and also we could plug the pose and 0 in the diagram, right? So here, to get a pose, actually pretty simple. Use the pole, and to get 0, you get 0, right? So when you use 0, you also get a game of the system too. So you get here. I want to show you. I just want to show you that system 1 and 2, they're the same, right? Although they represent it in different format, right? One is use TF, another one is ZPK. So P1 equal to the pole system 1, and P2 equal to pole systems 2. Right now I want to get the 0 and then the game from systems 1. So you get 0, the game from systems 2. Okay, save it, Control S, right? And then you're gonna run it. So you can see the game is right -0.2, 6, 6, 7, and then the pose, right? This -2, -1/3, -1/5, right? The same. Okay, this is the same P. The result from the first model and the second model the same. Okay, the game here. Well, the game what you get, the game K is the game define in the here in the pose and zero format right here. This game is not the one. This game is not the start state game, right? Start state game, you could use this command to get it. Right? The start state game actually equal to you set s equals 0, right, in the transfer function. Right, so the start state game is k equal dc game. Here we just put systems 1. Right, should be the same, so save it. System 1 and 2 should be the same, so start the game is 2. Okay, so if you want to try the second, you could change this to 2. Okay, maybe you could just change this to 2. The result should be the same. Control S, see, it's 2, right? Okay, good. The start state game is important again. You get the output. The change of the start state of output equal to start state game change times the change of the start state of the input. Okay, now I want to show you how to plot the pose and 0 using pzmap. Very simple. You just type the transfer function. So this one, the input, actually this input is transfer function. Okay, you have to represent the transfer function. Transfer function. Okay, you're gonna get this one, right? The clocks is for the pose, and the circle is for the 0, right? Again, remember, right? To get the system stable, the pose should be negative, right? Remember. So if the 0, if we have a 0, so this gets system stable. If we get a 0, positive 0, and then we will get inverse response. What's inverse response? Inverse response means the initial change of the output is opposite to the long-term change of output. So for example, this one initial change is of the output is decreases, but for the long-term one, the output is increases. Right? Okay, now let's show you. You just type p, just type here, just type pz map systems 1. Okay, save it. Save it and then you run it. So you can see here the result, right? This 3 poles and 1 circle. Okay, it's the same as this picture. Now I want to show you how to get the step response and also impulse response. So so this is the system, and this is the final time of the step change. Also, you could specify the sampling time point and for the simulation. So this t is the specified sampling time points. Okay, so now we get step. Right, this is the transfer function tf, and then this final time is 40 seconds, and then you plot it, right, and then a solid line and then a square, right, marker. So similarly, you could specify the sampling time point, and then just sampling time points here. You can still use step function here, right? Okay, now let me show you. So this is what you should get. This for the first figure. This for the second figure. Okay, now let me show you. So you're going to type. So I don't need to plug all this one. I don't need to do all this one. Right, and I just block them. So Control plus R. Just want to save some time in your simulation. Okay, now I want to get the output and the time. So Y is the output, T is the time. You get step, right? Change, and then you get system 1. The time for the simulation is 40 milliseconds. After that, you get plot the output and the right over the time. So here solid line, square, symbol, marker, right? And then the last bit is 2. Okay, there get S label. So you get time, minutes. Similarly, Y label. Here you get liquid level, unit is milliliter. Okay, so you could put a figure here. So means that we open a new figure, and then the figure will not be erased if I use another figure. I put figure here, right? Okay, now I specify the sample time point here. Alright, again from 0, increasing interval is 0.5 and then to 40. Let me put a semicolon here because I don't want to show all these time points. So here, put a semicolon here. I don't want to show T and Y. Okay. Now let's do this again. You get Y. Actually, I should use another Y. So I use Y sample was a bit better because I already used Y before. So I already use Y here, right? I now use Y sample. So I got step. This is the distance, right? This transfer function, and then put time sample. Okay, and then I just copy this one, change the time to time sample, Y to Y sample. Okay, and then I change the color to be the red color. Right there, this is black color, this is blue color. Okay, now I save it, then run it. So I should get 2 profile. So this is the last profile, this is the first profile, right? They're the same. Okay. So this one is the step change with the final time simulation, the simulation time. The second one is for the one I sample the output at this time I specify. Okay. So this step change response. So similarly for the impulse, it's very similar. You change step to the impulse. That's it. Now let me show you. So I just change. So in the program, so you close this one. Just change the step to impulse. That's it. So this impulse. This one should be impulse. Save it, run it, so you get similar result here, right? Okay. So you know how to get the step and impulse response. Now I want to show you if you want to use some more complicated input here. I want to show you, and you could use the function here is the general signal. Also, if you want to have a delay in the step change, you could use the step function t, the simulation time, and then t0 is the delay time, and also you could use LSIM to do all the simulation right after you generate the model. After generate this the input, right? Okay, now I will show you first I want to show the square input, square wave inputs here, because this is the one we're going to have. Okay, so you can see this, the P area is 4, right, of the signal, right, going up, then going down, right? This we call this square wave. Okay, and then so what we're gonna do is we're gonna do a simulation. We're gonna do a simulation for 10 seconds. Okay, and so this is the function you're gonna get. General the signal, so square the shape, and then 4 is the P area, right, of the wave. And time is this the time, the final time. So 0.1 is what? 0.1 actually is the here, because typically in the reality we don't get the ideal square shape, right? So typically here 0.1 means what? Means you see it is 4, right? So the middle of the P is 2, and then the rising point to the middle period here is 0.1. Okay, so you could change the shape of the square. Okay, so we save the input using the T and U. So after that you could put the input signal, right, and then also this transfer function, remember, so this transfer function times the input signal, then you get the output, right? So you could get the output, and then you can plot the output profile. Okay, now let's go back to the example, and then because I don't need to get the impulse response anymore, so I just block this. I might just block this one. Control and R. Now let's generate the signal here. So we get figure, right? Means that we open new figure, right? This the input signal we generate, and the shape of the signal is square. That is 4, this 10, this 0.1. Then we got plot T and U. And then we get S label, time, this minute, Y label, this is Q, kilowatt, right? Okay, then I want to show, so after that, after we specify the input, we want to use the model to predict the output, right? So we get a Y square, right? The output of the square input equal to LS, the simulation, right? L means linear, right? Linear simulation. SIM simulation. This the transfer function. So this the input signal U and T. So after that, we could plug the predict output from the model, right? From the transfer function. Square. And then red color square marker. Line width here is 2, and then we get S label and Y label. So we copy the S label should be the same, the Y label should be the liquid level, right? Y label is the liquid level, so Y label is liquid level. Here should be millimeters. Save it. Okay, run it. So here's the profile we're gonna get, right? Okay, so we're gonna have the input signal here and then the output signal. Okay, the same as this one. I'll show you. Okay, now what we show what we have so far is for the user's specified input. In most case scenario, we typically focus on the step change, right? So we get step, and then here, so now we want to get the step response with a delay is 5 minutes delay, right? The time unit is minutes. Okay. So here's the time, right? T sample is the time. So we have 5 minute delay. So with time and then the delay time. Okay, so after that we see this the step change we will get. This is the input, right? So after that we could similarly, right? We could get this transfer function, this the input time, and then input signal, and then also the input time here, right? Okay, very similar to the to what we have here in this example, right? Instead of use square, we use the step. So I copy the code and then I block this code. Okay. Okay, so I will change this one to step function, right? Then here I will change this one to, because we already have the time simulation, right? Simulate the sample time here, and then just delay 5 minute delay. Okay, and then so this one we call is yield step, right? And then actually this figure is not necessary, right? Because I already have one figure here. Okay, now let's just plot the time sample and then use step. Alright, so this is done. And then for the second one, like we need to use the updated time, and then this updated time is time sample, and then the updated input is use step. Alright. So other thing we don't need to change. Okay, now let's run the simulation. Something's wrong in my program. Let me check. Okay, so here means that the vectors must be the same length, so something wrong here. So this should be T sample, right? Okay, save it. Now I get it, right? So this is the input, and then this is the output. Okay, so you can see. Remember we have a positive 0. We have inverse response. Means what? Means, right, the output is going down first and then going up. For the long term it's going up, but at the beginning it's going down. So this is called inverse response, right? So based on the model, and we could predict the inverse response. We could predict that based on the 0 and the poles, and we could, right, determine whether the system has inverse response. Okay, now I want to show you this another. If you want to know more about the chances and characteristics, you use this viewer we call LTI viewer. LTI view, right? Can show you a lot of information for the time or frequency domain, and typically for the linear systems, right? And you could learn more about the the LTI viewer, and then by typing or the help for this LTI models, especially in the process control systems toolbox. Okay, now so to use this graphic user interface, you just type LTI view, right? So now I want to show you how to close all the figures. Just type close. Oh, that's it. All right. Okay, now because this is very simple, I just type LT view here, system 1, and then you can see so this is what you can have, and then you could see you could get a profile, right, for different input. Also you could get the characteristic, right, for example the settling time, the peak response, rise time, start state. So you could get a lot of information here. So so you can see plug, so you could change, just right click, and then you get, right, characteristic, right, you get settle time here, settling time here, show you, right, here, something like that. Okay, just play this around and you know more. Okay, the final function I want to introduce is step information. So for example, after you get the time, the output, and also the start state value from the step response, right? So we need to input the step response data. So and then also you need to specify the start state value, right? And then after that, you could use the step function to get all this information, right? Last time, settling time, minimum value and maximum value, and also the overshoot, undershoot, right? Okay, now I want to show you. So we already get the, right, this step response, right? This the time, right? And then this the output, right? And then start state value of the output is 2. Okay, but now you don't know, for example, the rise time, settling time, all this information. So what you can do is you just type. What you can do, you can just type the step information. So you can just type S step information. Again, you have to do a random summation to get the step response data, right? So let's see. Okay, I have to, so I might put this into the program. I need to get a step response first. Right? So here, yeah, actually this was a step, right? This is a step. Okay, this was a step. Okay, now save it and then run it. So you get all this information here. And then this one, right? Okay, so you get all the information of the step response. Must be the same as this one. Okay, so we're done with this module.